Hi. Now in this part of the question we're asked to use these results for sigma r squared and sigma r cubed going from r equals 1 to r equals n to prove this result, that the sum of r times r plus 1 times r plus 5 equals a quarter n times n plus 1, n plus 2, n plus 7 for all positive integers n. So how do we do this? Well, first of all, let's have a look at those results for sigma r squared and sigma r cubed. You can generally find these in any formula book. Now, first of all, I'd want to start by copying the question down. So we'll start with that then. We've got the sum of sigma r going from 1 to n of r times r plus 1 times r plus 5. And what I'd want to do next is to expand this bracket. So we'll keep the r at the front, and don't forget r going from 1 to n, and we'll just expand the two brackets there, and we're going to get r squared, and then we've got 5r plus another r, so that's going to be 6r, and then 1 times 5 is 5. Next, I would want to expand the bracket further, so we just multiply through by r, and we get r cubed, and then 6r squared, and then plus 5r. Don't forget we've got several terms here. We're summing over all of them, so we need to have that in brackets. Now what we can do next is to do the summation of each term. So this is going to be then the sum of r cubed, r going from 1 to n, and then when it comes to 6r squared, we can pull the 6 out of the summation, 6 sigma r going from 1 to n of r squared. And again we can do much the same kind of thing on the last term, 5 times the sum of r going from 1 to n of just r. And this is where we can now use these results up here. So the sum of r cubed, we can see down here, is n squared over 4 multiplied by n plus 1 all squared. And then for 6 r squared, 6 sigma r squared I should say, it's going to be 6 times this result. So we've got 6 multiplied by n over 6 to n plus 1, and then all that's multiplied by n plus 1. And for the last term it's going to be 5 times sigma r. Sigma r is up here as n over 2 multiplied by n plus 1. And you can see that in this second term here we can cancel out those two 6's. So all we need to do now is tidy this up. And I get a few clues from the fact of what we've got to prove here. We can see that we've got to have a quarter n and n plus 1, and I can see that I could force that out the front just by doing a quarter n and then n plus 1. If I force that out the front, then for this first term I've got the quarter, I've got an n, I need another n, I've got n plus 1 squared, I've got an n plus 1 here, so it's just got to be n times n plus 1. When it comes on to this term, I haven't got the quarter, so I'm going to need to multiply this by a 4. I've got the n out the front, and I've got n plus 1, so it's just going to be 4 bracket 2n plus 1. And then for the last one, to get the quarter on the bottom, I'm going to need to times top and bottom here by 2, so that means I'm just going to have a 10 there. I've got the n and the n plus 1 out the front. A quarter of 10 is the 5 over 2. Okay, so what do I do now? All I need to do is just simply clean up the square bracket. So we've got quarter n, n plus 1, and if I expand this out, I can see I've got an n squared term here, and then I've got 1n, and here I've got 8n, so that's going to be 9n. And then I've got 4 times 1 is 4, plus the 10 here is going to be plus 14. So n squared plus 9n plus 14. And that factorizes further. We'll just put the first part down here, quarter n, n plus 1. But when it comes to factorizing the quadratic here, 2 brackets, and we find that it is n plus 2 and n plus 7. Expand that out and you've got n squared plus 9n plus 14. And that is what we had to show. Alright?